Hello to all my professors. My name is Shrey Verma and I am a final year undergraduate student of the Department of Mechanical Engineering at IIT Kharagpur. I will be presenting before you my BTech project on motion and path planning of a legged mobile manipulator under the supervision of Professor Dilip Kumar Pratihar. Coming to the introduction of my project. A leg mobile manipulator is a hybrid robotic system in which a serial manipulator is mounted rigidly on a multi-legged mobile platform. For this project, I will be considering a six-legged mobile platform. A leg mobile manipulator or an LMM is preferred over a wheeled mobile manipulator or WMM for the following reasons. With WMM, it is much more difficult to accommodate unknown and uneven terrains. An LMM can achieve motion in a 3D space as compared to a 2D space restriction of WMM. An LMM is capable of achieving variable manipulator payloads and velocity conditions. The use cases of an LMM are dragging weights, valve operations, handling hazardous materials in disaster locations. And also, it can be used to help in hospitals, home search, and rescue operations. When it comes to a legged robot, a separate robotic arm is preferred over using one of the robot's legs for the reasons that there is a problem of lower workspace because the end effector is limited to smaller set of points and the robot lacks simultaneous locomotion and manipulation capabilities. Motion planning and control in an LMM are certainly difficult due to its high redundancy. For this project, a whole body planning and control scheme is implemented to calculate all the joint space parameters of the LMM in real time. The LMM will follow instantaneous end effector trajectory given by the user with the help of a computer keyboard. Inputs are updates to the end effector position given continuously at a set frequency, and the algorithm ensures singularity-free motion of manipulator and plans adaptive strokes for trunk body using optimization-based redundancy resolution. Coming to the model formulation, this is the LMM model as opened in SolidWorks. It has 6 legs and a robotic arm is attached to the trunk body. Each leg consists of 3 links where the joint angles of the ith leg is given by theta I1, beta I2 and beta I3. The joint angles for the manipulator arm are denoted by theta 1, alpha 2 and alpha 3. And the input is a array RE is equal to XE, YE and ZE. This figure shows the crab angle with respect to the global coordinate plane. The legs are numbered 1, 3, 5 on the left side and 2, 4, 6 on the right side of the platform. The assumptions taken here are that the height of the trunk body is constant during the motion. The trunk body is kept parallel to the XY plane. There is no change in the yaw angle due to omnidirectional motion and the slip between leg and ground is neglected. Now using this formulation, the derived kinematic equations are implemented directly in Gazebo. Now explaining the method and implementation. The first part is to create URDF from SLDASM. The SolidWorks assembly file opened is shown here. This file needs to be imported in ROS Gazebo. All the necessary coordinates which are defined earlier for all the joints are marked here and this is then exported to a URDF file using an add-in in SolidWorks. Next part is implementation of inverse kinematics. The left part shows the trunk body solution in which the theta I1, beta I2 and beta I3 equations are shown and the corresponding Ki1, Ki2, Ki3, Ki4, Ki5 and Ki6 values are calculated. And this is implemented in the solve hexapod method. Here di is the sum of link offsets of ith leg of the hexapod. Alpha naught, beta naught, theta naught indicates the vector of the platform's orientation in global frame. AI, BI, CI denotes the position vector from leg shoulder to its tip in global frame. Phi is the angle subtended by leg's first link with the local frame x-axis. Lij indicates the length of ith leg jth link from the platform. The right part shows the manipulator solution, in which theta1, alpha2, alpha3 is shown and the corresponding k1, k2, k3, k4, k5 and k6 is calculated. And this is implemented in the solve manipulator method. Here the D is the sum of the link offsets of the manipulator. Alpha naught, beta naught, theta naught indicates the vector that corresponds to the platform's orientation in global frame. EI, FI, GI denotes the position vector from the base of the manipulator to its end effector tip in global frame. Phi m is the angle subtended by the leg's first link with local frame's x-axis. Lj denotes the length of the jth link of the manipulator. Next I will explain the implementation of trajectory generation. Here we can see the trunk body solution. The trunk body velocity profile can be seen here, in which T0 to T1 is the ascending phase, T1 to T2 is the constant velocity phase and T2 to T3 is the descending phase. This is implemented in the TB trajectory method. The tip trajectory solution is such that when we talk about a coordinate frame which is fixed to the tip of the leg, the motion is restricted only to the x and z axis. The solution when such a case is occurring is done in the leg tip trajectory local.python file. And this local coordinate is then converted to the global coordinate frame using transformations in the leg tip trajectory local to global.python file. Next I will explain the gate planning for the robot. Here a fixed quadruped gate is considered. Here you can see the implementation of the quadruped gate in master.python file, in which initially the legs 2, 3, 4, 5 are supported, and then 1, 3, 4, 6 are the support legs, and then 1, 2, 5, 6 are the support legs. A image for the fixed quadruped gate in a hexapod can be seen here. However, the order of the support legs might be different. The next step is to solve the redundancy resolution problem, which is an optimization problem as given in the paper and is implemented in all of these methods of the redundancy resolution.python file. The next step is to find the adaptive stroke length. The TB time calculation.python file finds out the time t1 as given in the velocity time graph of the trunk body solution of the previous slide. Using this, the stroke length is calculated by finding T2, T3 and Vmax. All of these equations are used directly from the paper, and this coupled with the redundancy resolution together solve for the leg tip trajectory of the LMM. Now coming on to the simulation results, first we will understand the ROS file system. This shows the LMM model package in which the config folder contains the files for the name of the joints together with their PID controller value. The meshes folder contains the required STL files which are used by the URDF file, and the joint controllers.py file initializes the publisher and defines the subscriber for the joint states. The LMM SC package is the next package, in which the source folder contains the Python scripts for controlling the robot. Master.py file runs all the scripts in the modules folder, and the scripts in the module folders are basically the implementation of the paper. Here you can see the global coordinates and their mapping in gazebo simulation. Here the x-axis is marked in red, the y-axis is marked in green, and the z-axis is marked in blue. The keyboard mapping W and S moves the end effector along the z-axis of the LMM. The A and D keyboard mapping rotates the end effector about the z-axis, and the J and L mapping moves the end effector along the y-axis of the LMM. This is the video simulation result. This is corresponding to the WS mapping, the A and D mapping, the J and L mapping, and this is the stepping or the crab motion. Thank you.